In Lab 5, we will be modeling the boiling of water in my electric kettle, and then we'll compare the model with reality. We care about this problem because it's useful to know how fast your water will boil if you have some impatient tea drinkers as guests, or if you're in a cooking competition and you need the water to boil fast. In this lab, we'll first predict the time it takes to boil a liter of water using this specific heat formula. Then, we'll compare that to the actual time it took to boil the water. We'll revisit the prediction and see what happens if we work backwards to find what might actually be the initial temperature of the water. Finally, we'll discuss any ways to improve the experiment. The specific heat capacity formula, where Q is equal to mass of the object times the specific heat capacity of the object times the change in temperature of the object, finds the amount of energy needed to change the temperature of our system, with the system or object being the water inside the kettle. To find the time it takes the kettle to boil water, we first need to set some initial conditions. First, we'll assume that the temperature of the water will be around 20 degrees Celsius. Also, my kettle boils a liter of water, which also happens to be 1 kilogram. Then the specific heat capacity of water is 4.182 kilojoules over kilograms degrees Celsius. Also, we're assuming that the energy is coming from the actual kettle, whose wattage was listed on its back end as 1500 watts. So how long should the kettle take to boil the water? First, we find the energy needed to boil the water using the specific heat capacity equation. Since we assume the temperature of the water to be 20 degrees, that means the temperature needs to increase by 80 degrees Celsius to reach 100 degrees Celsius, which is the boiling point of water. And again, we have 1 kilogram of water, and 4.182 is our specific heat capacity. Together, the equation tells us that we need 334.56 kilojoules of energy to boil the water. Next, we know that the kettle is 1500 watts, which can also be written as joules over seconds. To convert to kilojoules over seconds, we can just add a period right here. And now to find the time, all we have to do is take our heat energy from before and divide that by the wattage to find our predicted time to be 223.04 seconds, or around 3 minutes and 43 seconds. Now, when I timed it in real life, the water came to a full boil at around 4 minutes and 7 seconds. One possible reason our calculations were off may be that we got the initial temperature of the water wrong. So let's work backwards and see what the temperature of the water might have been. If we work backwards, we get that the temperature of the water should have been 11.41 degrees Celsius. Overall, there are many ways that we can improve the prediction in this lab. This would include purifying the water to make sure that the specific heat capacity is correct for H2O, and also making sure that the quantity of water is exactly 1 liter, and we can do this using a graduated cylinder. And we could also probably make sure that we have a thermometer to measure the initial temperature of the water before we start, to see if there could be anything else affecting our system.